Hello, chemistry students. We're looking at one more section about oxidation-reduction reactions. And in this section, we're going to talk about how to balance these reactions. They're a little bit more complicated. Well, maybe a lot more complicated. But there's a special way that we balance redox reactions, and we're going to learn how to do that. Did you know the conservation of matter applies to oxidation-reduction reactions too? So when we're doing oxidation-reduction reactions, it's important that you remember we're transferring electrons. So the number of electrons lost must be equal to the number of electrons gained. It's a really, 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 really important concept, and that's what makes this a little bit more complicated because we're not only keeping track of individual atoms, we're also keeping track of the electrons and the changes that happen to in the charges and the different electrons. So let's do a little practice problem first. Balance this equation. We have cerium right here and tin right here, aqueous. And you'll notice cerium, aqueous cerium with a 4+ charge plus tin 2+ is producing cerium with a +3 charge and tin with a +4 charge. Here are the steps that we're going to follow when we balance redox reactions. The first step, we separate into half reactions. So the first thing we want to do, we want to look at the reduction half reaction and the oxidation half reaction. So we need to know what is the reduction half reaction and what is the oxidation half reaction. Cerium is going from +4 to a charge of +3. That means cerium is gaining an electron. So cerium is undergoing reduction. So let's write its half reaction down. Cerium 4+ is going to cerium 3+. Those are both aqueous, and that right there is our reduction half reaction. Let's look now at the oxidation half reaction. We have tin, right, going from a 2+ charge to a 4+ charge. So what is happening to tin? It is losing an electron, right? Loses actually 2 electrons. So since it's losing electrons, it's being oxidized. So let's write the oxidation half reaction down. Tin, aqueous, is going to tin 4+, aqueous. All right, now we need next to balance each of these half reactions. And in order to balance them, we need to look at electrons, okay? Look at this half reaction. Cerium is going from a 4+ charge to a 3+ charge. It is gaining an electron, and we need to account for that. So cerium is gaining an electron here. We need to write that into the equation, into the half reaction. So cerium that's 4+, it gains an electron, and that becomes cerium 3+. What about in the case of the tin oxidation half reaction? We're going from tin with a charge of 2+ to tin with a charge of 4+. Remember we talked about that just a minute ago. It loses 2 electrons. So in this case, the electrons are left over +2 electrons at the end. So we balanced each half reaction. The next thing we need to do, we just did that. We need to equalize the number of electrons gained and lost. What does that mean? Well, in this reaction, there are 2 electrons being lost. In this reaction, there's 1 electron being gained. We can't have 1 electron on one side of the equation and 2 electrons on the other side. So what are we going to do? We are going to equalize the number of electrons by simply multiplying this entire equation by 2. We're doubling that. And that way, both of these will be able to be combined together and will have equal numbers of electrons on each side. There will be an equal number gained and an equal number of lost. The same number on the left side of the arrow as on the right side of the arrow. So now we can do our final step and we can add the half reactions together. So what I'm going to do, I'm going to take everything on the left side of the arrows here and I'm going to write all of that down. So I have 2 cesium 4+, and I'll skip writing the aqueous for right now, plus 2 electrons, and then I'm also adding the tin here from that half reaction, plus the tin 2+. Now I'm going to look at everything on the right side of the arrows for both of the half reactions. I'm going to write all of this right here. So I have 2 cerium 3+ plus tin 4+ plus 2 electrons. There we go. I'm adding them together. Now, before I'm completely done, there's one more step I need to do. When I'm adding these equations together, if you'll notice, there is something the same on both sides, right? The number of electrons. Well, I can cancel those out because they are the same. So I can cross those out. They cancel on the left side and the right side. And if I had enough room, my final reaction that I would write, 2 cerium 4+ plus tin 2+ reacts and makes 2 cerium 3+ plus tin 4+. And that is my final balanced equation. Okay, here is another example. It's a little bit more difficult. We're going to add a little bit of complexity to it, but we are going to start with this reaction, and we need to balance it. This is just the net ionic equation. It is not balanced, but we are going to start with permanganate ion and an iron 2 ion. And that's yielding these products. First, separate into half reactions. Remember, we need to look at what is reduced and what is oxidized. To do that, we need to look at the oxidation states. Manganese here, we know that oxygen is -2. Remember our oxidation state rules that we assign. If oxygen is -2, that means the manganese is +7 because our total charge on this is a -1 for the entire ion is -1. So the manganese needs to be +7. The iron right here we know is +2. Over here, iron is +3 for its oxidation state, and manganese is +2. So let's look at that manganese when it's going from a +7 to a +2 oxidation state. It is gaining electrons. That means the manganese is being reduced. So let's write that down for our reduction half reaction. MnO4 minus. I'm not going to write the aqueous in there just for room. All of these are dissolved in water. We have that, and the half reaction, that is going to manganese +2. Our oxidation half reaction, we can see iron, oops, there it is, iron going from +2 to +3. That means an electron is lost, so it's being oxidized. So let's write that for our half reaction. Iron 2+ is going to iron 3+. Now, we need to balance each half reaction. This is going to be more complicated. I hope you can already see we have an oxygen right here in this half reaction on the left side, and there isn't one over here. Whoa, problem, right? These are the rules for balancing redox half reactions. And these are what you do each time. First, you need to balance the elements. We'll get to the electrons in a little bit, but we need to go and we need to look at the elements on each side of the equation and balance them. Let's look at manganese. There's one here and one on the right. That one's balanced. What about oxygen? It is not balanced, but look at our second rule. We balance oxygen using water. So in this case, we can add some water over here. That ends up giving us our oxygen, right? Here we have 4 oxygens. Here there's 1, so we're going to need to write a coefficient to give us 4 oxygens on the right side. Now we have another problem. We've got hydrogen over here and we don't have any over here. What are we going to do? Well, look at our next rule. Balance hydrogen using a hydrogen ion. So we get to add a hydrogen ion on the left side of the equation, and now I'm kind of running into a little bit of a problem here. There, I just paused the video and fixed it for us. I scooted over my little arrow here, added the hydrogen ion to the left side. How much hydrogen ion am I going to add? Well, how many hydrogens are there over here? 4 times 2 is 8. So I need to add 8 of them on this side. Now, I have balanced all of my elements. I must now balance the charge using electrons. So if I look at this side of the reaction, what is my total charge over here? I have 1 molecule that's a -1. I have 8 molecules that are +1. So I have a total charge here of +8. And over here, -1. That gives me on the left side of the reaction a total charge of +7. What about the right side of the reaction? Well, I have a +2 charge, and that's it. So the right side of the reaction is +2. So I am going to need to add 5 electrons to the left side of the equation. So I'm going to write 5 electrons over here. Now I am balanced. I've followed all these steps for balancing that half reaction. Now I need to balance the other half reaction. And maybe this can probably go a little quicker. It's more simple. We have iron 2+ and iron 3+. The atoms the elements are balanced, right? 1 iron and 1 iron. That's easy. I can go right now to balancing the charge. And I do that by adding an electron to this side. I have a 3+ charge and a minus charge. That gives me a +2 charge for this right side and a +2 charge on that left side. So I'm balanced for the oxidation half reaction. Now I can go to step 3, equalizing the number of electrons gained and lost. So let's look at the number of electrons in the reduction. We have 5 electrons on the left side. We only have 1 electron on the right side of the oxidation reaction. That means that we're going to need to multiply this by 5. Okay, and when we do that, see if it'll undo that for me. No, that means, let's just scribble this out, we get 5 iron and 5 iron and 5 electrons. Right there. Now we're going to add the half reactions together. So we take everything on the left side of both of those reactions, put them on the left side down here. Everything on the right side, put them on the right side here. And look at that. I wrote that down really fast. You can pause the video if you want to look at that. Make sure I got everything right. Wrote it all down correctly. We now can do some canceling, right? Remember, we can cancel out 5 electrons on the left side and 5 on the right. They're the same. They're identical. And we simply have this as our final balanced equation. Now, the last thing you need to do, and I'm going to say this, I didn't write it down here, but check your work. Make sure the elements are balanced and the charges are balanced. So we're going to look manganese, manganese, 4 oxygens, and go through, make sure all of the elements are balanced, and go through and make sure the charge is balanced. We have 8 positive charges plus 10 positive charges plus a negative charge there. That gives us 18 minus 1, 17. A +17 on the left side, And we should come up with the same on the right side. We have a +2 charge, and 3 times 5, that would be +15 charges there. So 15 plus 2 is +17 on the right side as well. Make sure you do that. That's really important. So now you try this. Here is a problem for you to do. It's a little bit of an application. When an automobile engine is started, it uses energy supplied by a lead storage battery. The battery uses an oxidation reduction reaction, exactly what we've been talking about. The reaction happens to be between elemental lead and lead-4 oxide. The unbalanced equation for a very simple version of this reaction is right here. You need to balance this equation using our half reaction method. So go ahead and pause the video, look back at the previous example and the different steps, and see if you can do this on your own. All right, now that you've had a chance to try it, let's see if we can work through this together. I'll go a little quicker and pause the video and just write some of the answers in for you as we go along. First, we separate into the half reactions. In order to do that, we need to assign oxidation states, and then look and see which is the reduction half reaction and which is the oxidation half reaction. Okay, so here I wrote those half reactions. Lead is going from lead-4. We know that because the oxidation state for oxygen is -2, so there's a total charge of -4 here, so lead must be +4, and that is going to lead +2. That means it is gaining electrons. It's being reduced. Here's the oxidation half reaction. We're going from lead with an oxidation state of 0 to lead with an oxidation state of 2+. So it is losing electrons, so it's oxidized. Now, step 2, balance each half reaction. For each half reaction, first, balance all the elements. And remember how we do that. We're going to use hydrogen, and we're not going to do hydrogen and oxygen. We will do that next, but first we'll balance the elements. The elements are balanced: lead, 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 lead. They're fine. Now we need to balance oxygen using water. So let's do that. So we simply add water. We need to add 2 of them so that we have 2 oxygens, because we have 2 oxygens on the left. Then we balance hydrogen using protons. So we can add protons to the left side here. And once again, we have 4 protons here, or 4 hydrogens there, so we need to have 4 there. We are done then balancing all of the elements. We now need to balance the charge using electrons in both of these cases. You see I have a +4 charge, 4 plus 1 charges, so that's +4 on the left side, and I have a +2 charge on the right side. That means that I will need to add 2 electrons to the left side. Now let's look at balancing the charge on the oxidation half reaction. I have a 0 charge on this side and +2 on this side. It means I'm going to need to add 2 electrons to the right side of the equation. Now I'm ready for my next step, which is to equalize the number of electrons gained and lost. Now this is really nice because we have 2 electrons on the left side, and to the right of the arrow, we see we have 2 electrons. So we don't need to multiply either equation by anything because the number of electrons gained and the number of electrons lost is the same. So now we can move on to step 4, add the half reactions together. Here is that final reaction, almost, except we get to cancel a few things out, right? 2 electrons, those cancel out on both sides. So then when I rewrite the equation, I can simply write that. That is my final balanced equation. Check. Check our work. Make sure that every element balances, that we have the same number on the left side as the right side, and make sure that the charges are balanced. Make sure the total charges on the left side equal the total charge on the right side, and then we're done. And so you can pause that, check them, make sure they're right. Advanced idea. There's an advanced idea for some of you. If you can come up with another advanced idea, please research that, look into it, find out more about redox reactions. I have a wonderful worksheet for you all to do, so make sure everybody does their worksheet and gets a little bit more practice doing this. These are kind of hard, but once you get the steps, they're really simple steps. It's a matter of just remembering everything that you need to do and all the different steps involved. So look forward to seeing you in class.